Hello and welcome. The date is December 18th, 2025. We are now less than 24 hours away from a moment that will likely be studied for decades, perhaps centuries. The object known as 3I Atlas is currently hurtling toward its closest approach with Earth, an event scheduled for 0602 Coordinated Universal Time tomorrow morning. If you have been following the mainstream coverage, you've likely heard it described as a fascinating comet or a rare interstellar visitor. But if you look at the raw astrometric data, the numbers that define its path through space, a very different, far more unsettling picture emerges. This is not just a rock tumbling through the void. This is an object that has executed a navigational feat so precise that the odds of it happening by chance are vanishingly small. Tonight, we are going to strip away the headlines and look directly at the orbital mechanics of this encounter. We are going to look at why 3I Atlas shouldn't be here, and yet here it is. Before we dive into the gravitational mathematics that make this object so anomalous, if you want to stay ahead of the breaking analysis on this flyby as new data comes in over the next 48 hours, make sure you hit that subscribe button and turn on notifications. We will be tracking this live. Now, let's look closer at the data regarding its arrival. When a massive object enters our solar system from interstellar space, it faces a gauntlet. It falls into the deep gravitational wells of the Sun and the giant planets, particularly Jupiter. Normally, this is a chaotic process. A random object, a rogue asteroid, or a cometary fragment will typically do one of two things. It will either crash into the star, consumed by the very gravity that drew it in, or it will be ejected chaotically, flung out on a random vector that pays no heed to the delicate plane of our planetary system. This is the standard model of interstellar interaction. It is messy, it is violent, it is random. 3I Atlas did neither of those things. Instead, this visitor executed what can only be described as a precise gravitational slingshot. It didn't just fall, it threaded the needle. It dove deep into the inner solar system, passing inside the orbit of Mars, using the Sun's gravity to gain immense speed. But here is the crucial detail that many initial reports glossed over. Its interaction with Jupiter. The object maneuvered along the very boundary of Jupiter's Hill sphere. For those unfamiliar with orbital dynamics, the Hill sphere is the region around a planet where its gravity dominates over the Sun. To skirt the edge of this sphere is to walk a gravitational tightrope. Pass too close, and you're captured or crashed. Pass too far, and you fail to gain the necessary assist to align your path. 3I Atlas passed on a knife's edge. This near miss was not a clumsy brush with a gas giant. It was a maneuver that avoided capture while keeping the comet on a narrowly defined trajectory. It effectively used Jupiter as a fulcrum to pivot its path. The result? It entered the inner solar system on a path closely aligned with the ecliptic plane, the flat disk where Earth and the other planets orbit. The probability of a random interstellar object entering the solar system on a path so closely aligned with the ecliptic is calculated at only 0.2%. That is 0.2%. Let that sink in. If you were throwing a dart at a dartboard from a mile away, and you not only hit the bullseye, but hit the exact center of the pin holding the bullseye in place, you might begin to understand the precision we are seeing here. Unlike a random asteroid, which would approach from any angle, from above or below the solar system, this object slid in sideways, perfectly matching the traffic flow of our planets. It demonstrates a trajectory far more precise than expected from natural gravitational interactions alone. So, what does this actually mean? It means we have to ask a difficult question. Is this precision the result of a one-in-a-million cosmic lottery win? Or is it evidence of something else? When we see a spacecraft from Earth perform a gravity assist, like the Voyager probes or Cassini, we know it requires thousands of hours of calculation and precise thruster burns to hit that keyhole in space. 3I Atlas hit a similar keyhole. It utilized the gravitational landscape of our solar system with an efficiency that mimics intelligent navigation. This brings us to the concept of the gravitational needle. The object's path suggests it wasn't just falling, it was aiming. The energy required to correct a trajectory after entering the solar system is immense. But if you line up your approach vector perfectly while you are still light years away, you can use the gravity of the stars and planets you pass to do the work for you. This is known as a ballistic capture or a low-energy transfer, but it requires knowledge of the system you are entering. A rock does not know where Jupiter is. A rock does not know the mass of the Sun. A rock simply obeys gravity. 3I Atlas obeyed gravity, but it did so in a way that maximized its stability and alignment with Earth. We must also consider the speed. It gained velocity from the Sun, yes, but the interaction with Jupiter was the braking mechanism that refined its vector. It's a push-pull dynamic that stabilized its orbit relative to the ecliptic. If it had been slightly faster or slightly slower, or if its angle of entry had been off by a fraction of a degree, it would currently be millions of miles away from where it is now, likely heading out of the system at a steep angle, invisible to us. Instead, it is here. It is right here, passing us at a distance that allows for high-resolution observation. This contradicts what we previously thought about interstellar comets. When Oumuamua passed through in 2017, it was tumbling, erratic, and on a high-inclination orbit that took it quickly away from the planets. It was like a stone skipping across a pond. 3I Atlas is like a submarine diving into the channel. The difference in orbital geometry is stark. The 0.2% probability is a statistical red flag that we cannot ignore. In science, when you see a number that low, you don't just shrug and say, "Lucky guess." You look for a cause. You look for a mechanism that biases the outcome. And this is just the beginning of the anomalies. If the trajectory was the only oddity, we might be able to write it off as a freakish roll of the cosmic dice. We might say, well, the universe is big and strange things happen. But the trajectory is merely the delivery system. The package itself, the comet, the object, whatever it is behaving in ways that defy the physics of ice and rock. As we look at the tracking data coming in from observatories around the world, we are seeing that this gravitational needle didn't just thread the path to get here. It is now orienting itself. A rock tumbling through space has no front or back. It has no preference for where it looks. But 3I Atlas does. As we prepare to analyze the rotational data in the next segment, Keep this trajectory in mind. We are dealing with an object that arrived with intent. It is not a drifter, it is a visitor that knocked on the door before entering. The precision of its arrival sets the stage for the precision of its behavior. We have established that it is where it shouldn't be, statistically speaking. Now, we need to understand why it is acting the way it is. Because, as it turns out, the way 3I Atlas moves through space is even stranger than the path it took to get here. As we established in our analysis of the trajectory, 3I Atlas arrived in our inner solar system with a navigational precision that defies the 0.2% odds of a random encounter. It threaded the gravitational needle of Jupiter and the Sun to place itself on a stable, ecliptic-aligned path. But if the path was the only anomaly, we might still cling to the lucky rock theory. However, as we zoom in on the object itself, the behavior of 3I Atlas dismantles that theory piece by piece. We are now facing what researchers are calling the 15th Anomaly, and it is perhaps the most baffling of them all. Let's look closer at the data regarding the object's rotation. Comets rotate. Asteroids rotate. This is basic mechanics. Nothing in space sits perfectly still. When a natural comet rotates, its surface is exposed to the sun in a cycle. Day, night, day, night. As the sunlit side heats up, ices sublime, creating jets of gas and dust. When that side rotates into darkness, the jets usually die down or sputter out as the temperature drops. It is a chaotic, rhythmic process, like a sprinkler spinning in a garden. 3I Atlas is not behaving like a sprinkler, it is behaving like a spotlight. Observations reveal that while the comet itself is rotating, its active jet remains pointed toward the sun with an accuracy of 8 degrees. Imagine a spinning top. Now imagine painting a dot on one side of that top. As the top spins, the dot should point at you, then away, then at you, then away. But with 3I Atlas, it is as if the dot, the jet, is sliding across the surface of the object in real time to compensate for the rotation, keeping itself locked on the sun. Or, alternatively, the internal mechanism driving the jet is selectively activating only the specific vents that are currently facing the star, switching them on and off with computerized precision as the object spins. This is the 15th anomaly. The jets are active only when facing the sun, even though the bases of these jets must at times be on the night side. For a natural object, this is physically counterintuitive. If a vent rotates to the night side, it should cool down. If it rotates back to the day side, it takes time to heat up again. There is a thermal lag. 3I Atlas shows no such lag. It maintains a continuous, high-pressure stream directed at the sun, regardless of its rotational phase. Such behavior implies sophisticated insulation or internal control that is extremely difficult to reconcile with a natural comet. It suggests that the interior of the object is not a solid block of ice, but a structure capable of managing heat flow or directing output. But the anomaly gets deeper. We have to look at what happened after perihelion, the point of closest approach to the sun. Before perihelion, the object had one active jet facing the sun. As it swung around the star, the geometry changed. The side that was facing the sun began to turn away. In a natural scenario, the jet should have pointed away, or the comet should have tumbled. Instead, a second jet on the opposite side of the object activated. And just like the first one, this new jet locked onto the sun, again with that same 8-degree precision. So, what does this actually mean? It means the object effectively switched engines. It turned off the forward thruster and turned on the rear thruster, or vice versa, depending on the orientation, to maintain a constant relationship with the solar wind. The probability that a natural object would orient its poles toward the sun twice in a row, once inbound, once outbound, is roughly 1 in 40,000. I want to pause here and ask you a question, because this is the part that keeps astronomers up at night. If you saw a drone spinning in the air, but its camera stayed perfectly locked on you the entire time, would you assume the wind was blowing it that way? Or would you assume it was tracking you? Let me know in the comments below. Do you think a 1 in 40,000 chance is just a coincidence, or is this evidence of a mechanism we don't understand? This sunward lock is not just a curiosity, it is a smoking gun for internal complexity. The rotation axis of 3I Atlas was aligned within 8 degrees of the Sun during July through August 2025. This alignment implies that the base of the new anti-tail jet, the one that turned on after perihelion, was sitting in total darkness on the night side for months before it activated. And the base of the old jet, the one active before perihelion, rotated into the night side and immediately shut down. For these jets to be active only when facing the sun, they must be well insulated on the night side. If they weren't insulated, the heat would bleed through the object, and you'd get outgassing from all sides, creating a messy, diffuse cloud. We don't see a cloud. We see a beam. This requires a thermal barrier that prevents the sun's heat from soaking into the core of the object, keeping the volatile materials frozen until the exact millisecond they are needed. This is the non-trivial nature of the 15th anomaly. Nature rarely insulates this well. Nature tends toward equilibrium. 3I Atlas is fighting equilibrium. Why would independent bases near opposite poles of the rotation axis produce tightly collimated jets with similar opening angles? That remains unexplained by standard cometary models. If you have a pocket of ice on the North Pole and a pocket of ice on the South Pole, they should be different. They should have different shapes, different purities, different melting rates. Yet here, they are producing identical focused outputs. It's as if the object has symmetrical exhaust ports. This connects to the anti-tail phenomenon we will discuss later, but for now, focus on the orientation. We have an object that arrived on a precise trajectory, anomaly number 1, and is now maintaining a precise orientation, anomaly number 15. It is tracking the sun. It is reacting to its position in the solar system. And if the movement is strange, the stuff coming out of these jets is even stranger. We usually expect comets to be dirty snowballs, mostly water, some dust, maybe a little carbon dioxide. But when the ALMA telescope turned its dish toward 3I Atlas, it didn't see water. It saw something that looks a lot more like a chemical factory than a melting iceberg. Building on this, we need to examine the exhaust of this engine, because if 3I Atlas is a machine, or at least a manufactured object, its fuel source should give it away. And the chemical signature we have just detected is unlike anything we have ever seen in a natural comet. Given what we now understand about the object's impossible trajectory and its uncanny ability to keep its jets locked on the Sun, we must turn our attention to the material being ejected. If this were a standard comet, we would expect the spectral signature of water vapor, carbon dioxide, and simple dust. It's the recipe for a dirty snowball, the standard model for comets since the 1950s. But 3I Atlas is not following the recipe. When the Atacama Large Millimeter Submillimeter Array, known as ALMA, in Chile pointed its high-frequency receivers at 3I Atlas, the data that came back sent shockwaves through the astrochemical community. The telescope did not detect the overwhelming signature of water ice sublimation that characterizes 99% of cometary activity. Instead, it detected complex organics. Specifically, the analysis revealed a methanol to hydrogen cyanide ratio of 124:1. To put that number in perspective, typical comets have a ratio that is orders of magnitude lower. Finding this much methanol relative to hydrogen cyanide is like finding a car exhaust that is emitting pure high-octane fuel vapor instead of carbon monoxide. It implies a chemistry that is carbon-rich and oxygen-poor in a way that is rare for primordial ices. But the ratio itself is not the most startling part. It is where the methanol is appearing. In a normal comet, molecules sublime from the nucleus and drift away. They are born at the surface. But in the tail of 3I Atlas, the concentration of methanol actually increases as you move away from the nucleus. Methanol appears inside the tail as the comet moves away from the nucleus, indicating active chemical reactions rather than simple sublimation. This means the tail is not just a passive cloud of gas, it is a dynamic chemical environment. Something is reacting. Something is being synthesized or released from a precursor molecule as it flows downstream. This looks less like a melting ice cube and more like the plume of a chemical engine, where combustion or reaction byproducts are still forming milliseconds after ejection. This chemical anomaly provides the context for the physical force we are observing. We are seeing an anti-tail extending over 500,000 kilometers toward the Sun. Now, anti-tails are a known optical illusion in astronomy, usually caused by heavy dust particles left behind in the comet's orbit that appear to point sunward due to viewing geometry. But this is not an illusion. This is a physical jet. To create a structure this long and this straight, pointing directly against the solar wind, you need power. The particles in this anti-tail are moving at speeds exceeding 130 meters per second. This is the crucial detail. Ordinary ice sublimation, the gentle fizzing of a comet warming up, produces ejection speeds of perhaps a few meters per second, maybe tens of meters per second in extreme cases. It is a drift, not a blast. 130 meters per second is a thrust. This velocity is far beyond what ordinary ice sublimation could produce. It resembles a retro thrust jet. If you were piloting a spacecraft and wanted to slow down or stabilize your orientation against the pressure of the Sun, you would fire a thruster exactly like this. The high velocity implies a nozzle. It implies pressure. It implies a mechanism that accelerates the gas, rather than just letting it float away. When we combine the chemical data with the velocity data, the picture becomes clearer. We have a fuel, the complex organics and methanol precursors, and we have an exhaust velocity, 130 meters per second. This is the definition of a propulsion system, however primitive or advanced it might be. Whether it is a natural organic engine created by some freakish geological process or an artificial thruster, the effect is the same. It is generating a force vector that is altering the object's motion. This explains why the trajectory is so precise. It explains the knife's edge flyby. The object is not just falling, it is pushing. But there is one more layer to this mystery, and it is perhaps the most visual and undeniable piece of evidence we have. We have talked about the chemistry, and we have talked about the speed. Now we need to talk about the shape, because a gas cloud expanding into a vacuum should spread out. It should diffuse. It should look like a puff of smoke. The anti-tail of 3I Atlas does not look like smoke. It looks like a beam. It is tightly collimated, maintaining its narrow shape over 500,000 kilometers of space. This is the 14th anomaly, and it is the one that has experts like Dr. Eric Keto and Dr. Frank Lokian scratching their heads. How do you get a cloud of gas to stay together in a straight line for 500,000 kilometers? This connects to the structural integrity of the object. If the jet is this narrow, the opening it comes from must be incredibly specific. We are not looking at a crater. We are looking at a tube. Building on the discovery of the high-velocity chemical engine driving the anti-tail, we arrive at the most visually striking aspect of 3D Atlas, the shape of the jet itself. In fluid dynamics and rocketry, the shape of an exhaust plume tells you everything about the nozzle that created it. A wide, messy plume suggests a rough opening. A tight, needle-like plume suggests a long, engineered barrel. The 14th anomaly further underscores the object's unusual characteristics. We are witnessing the appearance of tightly collimated jets forming the anti-tail in the sun's direction. This phenomenon has been observed both before and after perihelion, which, as we noted earlier, is statistically bizarre. But the geometry of the jet itself is where the math breaks down for the natural model. The probability of these jets forming this specific shape at random is calculated at 0.0000025. That is 25 chances in a million. The collimation of these jets is accurate to within 8 degrees over a distance of 500,000 kilometers. This was confirmed in images taken just 3 days ago on December 15, 2025. To maintain a beam that tight over that distance is highly unlikely naturally. Gas wants to expand. In the vacuum of space, entropy dictates that a cloud should dissipate. For a stream of particles to stay this focused, it must be imparted with a very specific angular momentum and velocity vector at the source. Experts Dr. Eric Keto and Dr. Frank Lokian have provided crucial insights on this phenomenon. They describe the pre-perihelion anti-tail not as a tail, but as a sunward jet near the rotation axis, spinning like a rifle bullet along its direction of travel. This analogy is perfect. A rifle bullet spins to maintain stability. This jet appears to be doing the same. The spin stabilizes the stream, preventing it from breaking up. Analysis of Hubble space. Telescope images from July 21, 2025 gives us the hard numbers. The anti-tail is about 10 times longer than it is wide. Specifically, The long axis extends toward the Sun, twice as far as its width, but when viewed at the calculated 10-degree angle relative to the axis, the true length-to-width ratio is approximately 11.6. This is a tube. It is a cylinder of gas. Recent images confirm a sunward jet with an opening angle of only 6 to 8 degrees. Frank Lokian emphasized that while sunlight can collimate typical cometary tails, the solar wind pushes the dust back. A tightly collimated anti-tail, pointing into the solar wind, is extremely difficult to produce. Any large ice field on the surface of a comet would generate a broad forward plume, like steam rising from a lake. It would be a diffuse fog. Instead, we see a narrow beam. Hypothetically, a deep ice pocket shaped like a gun barrel could emit a beam. If you had a deep hole in the comet and the sun shone straight down it, the gas would rush out in a column. But here is the problem. Sunlight would only illuminate the bottom of that hole briefly as the comet rotated. It would be a flash, not a continuous stream. And yet the stream is continuous. This implies that the gun barrel is tracking the sun, or the mechanism is not dependent on direct sunlight hitting the ice at the bottom of a hole. If the collimated anti-tails pointing toward the sun are technological, they could serve functions that have nothing to do with being a comet. They could serve for propulsion, although, as we noted, the thrust is low for a rapid maneuver. More likely, they could act as directed shields against sunlight and solar wind. If you are a technological probe filled with sensitive electronics or biological samples, you do not want to be cooked by the sun at perihelion. You might fire a dense stream of gas toward the star to create a plasma bow shock, a physical umbrella that deflects the radiation. Or, theoretically, they could be directed weapons. While this is unlikely given the lack of hostile action, a high-velocity particle beam is effectively a sandblaster in space. But we see no target. The target is the sun. So, what does this actually mean? It means we have an object that is shaped like a nozzle, acts like a nozzle, and produces a jet that defies the laws of natural diffusion. We have the trajectory, we have the lock, we have the chemistry, we have the shape. Now we have to put it all together. When you stack these probabilities, the 0.2%, the 1 in 40,000, the 0.000025, you reach a number that is no longer statistical noise. You reach a verdict. We have examined the trajectory, the rotation, the chemistry, and the structure of 3I Atlas. Now we must step back and look at the full picture. In science, a single anomaly is a curiosity. 2 is a coincidence. 3 is a pattern. 3I Atlas presents us with a cascade of impossibilities that, when taken together, scream that this is not a natural object. The combination of rare geometric coincidences strengthens the argument for extraordinary behavior. Let's do the math. Considering the 5-degree trajectory alignment, a probability of 0.002, the 8-degree rotation axis alignment with the Sun, 0.005, and the probability of 2 independent bases producing tightly collimated jets to within 8 degrees, 0.000025, the net probability is approximately 1 in 4 billion. 1 in 4 billion. If you bought a lottery ticket every day for 10 million years, you might hit these odds once. And this calculation does not even include the additional anomalies we haven't fully explored today, such as the disproportionately high nickel content detected in the spectral analysis. The composition resembles industrial alloys, stainless steel, or Inconel, more than it resembles the silicate dust of a typical asteroid. These anomalies raise fundamental questions. What is 3I Atlas? Is it a derelict probe, a functioning surveyor, a piece of interstellar debris from a destroyed civilization? And perhaps more disturbingly, why is there so little curiosity from self-declared comet experts regarding its nature? The mainstream silence is deafening, but the data speaks for itself. For those of you who want to see this history-making object with your own eyes, the window is closing fast. The comet will reach its closest approach on December 19th at 0602 Coordinated Universal Time. Here is when you need to look, depending on where you are. In Europe, observers in London can see it at 0602 Greenwich Mean Time. In Paris, Berlin, and Rome, the time is 0702 Central European Time. In the United States, the encounter happens in the early hours or late evening of December 18th. New York sees it at 0102 Eastern Standard Time. Chicago at midnight 0002 Central Standard Time. And for the West Coast, Los Angeles, your best viewing time is 2202 Pacific Standard Time on December 18th. It is located in the constellation Leo, positioned just below the bright star Regulus. This makes it relatively easy to find if you know where to look. However, do not expect to see a blazing streak across the sky with your naked eye. At magnitude plus 12, it is faint. Observing requires a telescope of at least 8 inches or 200 millimeters aperture. If you have a backyard telescope, now is the time to dust it off. For those without equipment, do not worry. The Virtual Telescope Project will provide live coverage starting at 0400 Coordinated Universal Time, which is 2300 Eastern Standard Time on the 18th. I highly recommend tuning in, seeing this object live. Knowing what we now know about its impossible nature is a profound experience. 3. I-Atlas is not just another comet. It is a historic interstellar visitor demanding close observation. It has challenged our models, defied our statistics, and perhaps, just perhaps, given us our first glimpse of technology that is not our own. If you found this deep dive valuable, please hit the like button. It helps this scientific content reach more people who are asking the same questions we are. And don't forget to subscribe for updates as we analyze the post-flyby data. The story of 3I Atlas is far from over.